Voyager 1, humanity's farthest object in space, encountered difficulties in November 2023. After over 45 years of travel, the spacecraft struggled to transmit data back to Earth. Suddenly, it sent a perplexing pattern of ones and zeros that defied comprehension. This prompted engineers and scientists to take action, attempting to diagnose and resolve the problem from a distance of 24 billion kilometers, or about 15 billion miles. Their goal is to ensure this historic mission continues to yield invaluable insights from its epic journey through space. The jumbled data transmission raised questions about the cause. Was it a minor glitch or a major malfunction lurking beneath the surface? Most importantly, given the spacecraft's age and vast distance, was it feasible to address this issue? To answer these questions, let's delve into every challenge, issue, and glitch Voyager 1 and 2 have encountered since their launch.
Yet both missions went seriously wrong, only moments after taking flight.
We thought that we'd lost the spacecraft.
Before the long space exploration of Voyagers 1 and 2 began, Voyager 2, the first of the two probes to launch, faced a system error right after the spacecraft carrying the probes was launched into the sky.
Voyager's programmers had taught the spacecraft that if it sensed anything unusual, to switch to backup systems. And that's exactly what had already occurred. Engineers call this fault protection.
The Voyager spacecraft is equipped with a fault protection system that includes multiple routines capable of recovering from specific potential mission-threatening events. These routines are designed to handle various failures and ensure the spacecraft's survival. Voyager 2 rose from Earth at 10:29 a.m. Eastern Daylight Time on August 20th, 1977, to begin its voyage of exploration, but only after having suffered a double computer failure as its Titan IIIe Centaur launch vehicle sat on Launch Complex LC-41, which is today known as Space Launch Complex SLC-41 at Cape Canaveral, Florida. This launch complex has supported dozens of space missions, boosted by a range of Titan and Atlas rockets since December 1965, and most recently hosted the launch of the latest Global Positioning System, GPS, satellite atop an Atlas V on August 1, 2014. Even after the computer problems were rectified, Voyager 2 suffered another glitch as the Titan IIIe Centaur roared into the clear Florida sky. These glitches appear to have been caused by the spacecraft suffering robotic vertigo as it rolled and pitched in its ascent trajectory. It also separated from the booster's final stage too quickly, which convinced its onboard computers that its primary attitude control system had failed. The fault protection system kicked in, starting its reconfiguration process. Fortunately, its attached Centaur upper stage remained in control, autonomously correcting the error before releasing the spacecraft. At length, matters settled down. 71 minutes after leaving Cape Canaveral, Voyager 2 fired its solid propellant motor for 45 seconds to heave it out of Earth and onto a course for its first planet, Jupiter. Still, none of the flight controllers at the Jet Propulsion Laboratory, JPL, in Pasadena, California, could breathe easily, for more trouble was in store. Less than 2 minutes after the conclusion of the Trans-Jovian burn, Voyager 2 sensed and reacted to another orientation error. It had been pre-programmed so that if it encountered difficulties, it was to safe itself and reposition its high-gain antenna toward Earth. For another 1.5 hours, it struggled to stabilize itself. The procedures NASA put in place to protect the spacecraft, far from Earth, had inadvertently tripped only hours into the mission. Voyager 2's brain seemed a little too sophisticated for its good. Other unwanted surprises on the first day of the flight included disturbing telemetry, which indicated that the scan platform, carrying an array of scientific instruments and batteries, was not deployed correctly. Fortunately, this was a false alarm caused by a faulty sensor. Voyager 1, however, was not quite so lucky when it rocketed into space, also atop a Titan IIIe Centaur from LC-41 at 8:56 a.m. Eastern Daylight Time on September 5, 1977. During the Voyager 1's launch, Charlie Colhars, the navigation expert on Voyager throughout its mission, was seated in front of a console and expressed concern, saying to John Cassani, Voyager project manager then, "This doesn't look promising." John asked, "What's the issue?" Charlie responded, "I don't believe we'll reach the required velocity." Although they were unsure of the reason, it became apparent after the second stage burn that they hadn't achieved it. Nevertheless, the Centaur guidance system was in control and recognized the velocity deficit. It extended the burning time of the Centaur engines, allowing them to compensate for the shortfall. It was truly remarkable. Just 2 weeks after Voyager 1 lifted off, it captured a remarkable departing image of Earth and our Moon from a distance of nearly 7.5 million miles, or 12 million kilometers. This photograph marked the first time in human history that our home planet and its only natural satellite appeared as crescents in a single frame. However, during this initial mission phase, Voyager 1 encountered a problem when its scan platform jammed. Although engineers managed to free it, they proceeded cautiously, handling the situation delicately for several months. As the team behind Voyager 1 worked diligently to maintain its trajectory, their counterparts overseeing Voyager 2 encountered their challenges. Meanwhile, the Voyager 2 team faced challenges shortly after its launch in August 1977. One of the hydrazine maneuvering thrusters pointed in the wrong direction, causing fuel to be sprayed toward the spacecraft. This did not cause physical damage, but it had the same effect as using a high-pressure jet washer, resulting in Voyager 2 drifting slightly off course. Correcting this issue required additional use of hydrazine, and eventually the problem was resolved. However, the sensitivity of Voyager 2's infrared imaging spectrometer became seriously degraded by December 1977 due to the crystallization of bonding material that held its mirrors in place. This caused the mirrors to become warped and misaligned. Consequently, the instrument's sensitivity diminished. Fortunately, a flash-off heater was employed to reverse the evaporation process, and the instrument returned to its pre-flight sensitivity. A more serious problem soon overshadowed these glitches. In April 1978, nearly 8 months into the mission, a series of issues caused Voyager 2 to lose control of its leading radio receiver, effectively rendering it deaf in one ear. The first problem occurred when the spacecraft's 7-day events timer reached 0 without receiving a command from the ground. In response, Voyager 2, as programmed, assumed a failure and switched to its backup receiver. Although corrective instructions were sent from Earth to revert to the primary receiver, initially the spacecraft did not respond. During this period of communication difficulty, another problem emerged. Each radio receiver was equipped with circuitry designed to detect incoming signals' frequency and adjust accordingly automatically. However, a tracking loop capacitor, a crucial component of this circuitry, had failed, likely due to an electrical short. As a result, the backup receiver would only respond to commands transmitted at precisely the correct frequency. Voyager 2 effectively became tone-deaf regarding JPL's planned signals, even before it arrived at its first planetary target, Jupiter, on July 9, 1979. However, Controllers had already learned to communicate with the spacecraft on different frequencies by that time. JPL team could routinely predict the precise frequency at which Voyager would hear a signal and adjust its transmissions accordingly. Calculating the precise frequency was a significant challenge because engineers had to account for the motion of the transmitting station on Earth's rotating surface, which was also orbiting the Sun, and Voyager 2's movement. Additionally, the spacecraft's receiver frequency fluctuated due to changes in ambient deep space temperatures. A mere 1 degree Celsius, 33.8 degrees Fahrenheit difference could cause the frequency to shift by up to 96 Hz. After considerable effort, a breakthrough was made and contact was re-established. However, during the switching from the backup to the primary receiver, an electrical short occurred, blowing both fuses in the primary receiver and rendering it inoperable. This posed a significant threat to the mission's success. Nevertheless, extensive reprogramming efforts on Earth and weeks of transmission to the spacecraft eventually stabilized Voyager 2 for its continued exploration mission. Trouble arose again about 100 minutes after Voyager 2 swept close to Saturn on August 25, 1981. Some of the gearing for the scan platform seized up. This platform carried Voyager's optical instruments, aiming and panning them to avoid blurring pictures taken as the spacecraft zipped past a planet or one of its moons. The jammed gears crippled Voyager 2 during its Saturn flyby. Yet 2 days later, the gearing was free again. Engineers had been slewing the platform at its highest rate of 1 angular degree per second. This drove the lubricant out of the stuck bearings, which seeped back in during the 2 days' rest. JPL engineers then understood how to cope with this potentially crippling problem. They had extensively studied it with similar equipment in the laboratory. They were confident that it wouldn't seize up if they didn't drive the platform at its highest slew rate. Indeed, Miner noted that they had used the platform extensively at slower slew rates since February 1983, with no hint of stickiness. After successfully exploring Jupiter and Saturn, Voyager 2 was approaching its first ever encounter with the ice giant planet Uranus. By this time, the scan platform responsible for moving Voyager's camera was prone to seizing up. Transmitting instructions to the spacecraft became complex, as the primary receiver was no longer operational and the backup was only partially functioning. Additionally, receiving a signal back from Voyager posed a challenge. The one-way transmission time now took 3 hours. When Voyager zoomed past Uranus at 10 a.m. on January 24, 1986, Pacific Standard Time, it found itself a long way from home, nearly 2 billion miles or 3,218,688,000 kilometers, twice the distance it was when it visited Saturn. Retrieving Voyager's invaluable data intact over such a vast distance posed a new challenge not initially accounted for in the mission plan. The signal from Voyager, which travels from Uranus in about 2 hours and 45 minutes, would be too faint for JPL's global network of powerful tracking antennas to receive adequately. To overcome this obstacle, Australia's Parkes Radio Observatory stepped in to assist. Additionally, communications engineers devised a method to encode Voyager's image data that required the spacecraft to transmit at most 40% of the usual number of data bits per image. Under the old method, it would have taken 8.8 minutes to send a single picture from Uranus, compared to 2.4 minutes per picture at Saturn. With the new encoding, Voyager could transmit a picture every 4 minutes. Given Voyager's brief window near Uranus, scientists aimed to capture as many pictures as possible to maximize their research opportunities. Avoiding motion blur in the pictures from Uranus was even more challenging than with those from Saturn. Panning the scan platform couldn't fully compensate for motion at all the photo targets as the spacecraft whizzed past at 45,000 miles or 72,420.48 kilometers an hour. Also, at twice Saturn's distance from the Sun, the light was 4 times dimmer at Uranus than at Saturn. This meant longer exposures per picture than Voyager engineers had used before. Todd Barber is a propulsion engineer who has been involved with the Voyager mission since its launch. He is an expert in propulsion and has contributed to the mission's success. He has been a part of the Voyager team since he was fresh out of college, and his career began with the Voyager mission in 1979. During an interview, he said, "Well, it's like keeping an old car running. They are geriatric spacecraft according to NASA standards, and it's been the hardest engineering I've ever done in my entire career. But that means it's the most fun because engineers love a challenge." During their journey, both Voyager spacecraft received a series of updates and patches to address issues and improve their functionality. In 2010, Voyager 2 experienced a glitch that impacted its operations. The glitch in its flight data system affected the formatting of data sent back to Earth. NASA's Jet Propulsion Laboratory, JPL engineers worked to resolve this issue. Sometime between April 22nd and May 17th, 2010, a single bit in Voyager 2's memory flipped from 0 to 1, causing a change in the science data pattern returning from the spacecraft. This bit flip disrupted the data transmission, preventing mission managers from decoding science data. A software update was sent to Voyager around May 23, 2010, to correct this issue and flip the faulty bit back to its correct position, restoring the spacecraft's proper functioning. Engineers at NASA's Jet Propulsion Laboratory traced the issue to the Flight Data System computer, which packages data for transmission back to Earth. Years after that memory flip error, the fault protection system was activated again nearly 20 years after the code was written, and this time it was not for Voyager 2, but for Voyager 1. In 2014, the fault protection system feature proved critical in saving Voyager 1 when a piece of hardware malfunctioned. The spacecraft's ability to automatically reboot allowed Voyager to recover, ensuring the continued operation and resilience of Voyager 1. On Tuesday, November 28, 2017, after 37 years of inactivity, engineers successfully fired up a backup set of thrusters on Voyager 1, the farthest human-made object in interstellar space. This decision was made because the original thrusters used for orientation on Voyager 1 were degrading, so engineers revived backup thrusters designed for trajectory correction. These hadn't been used since 1980, but were successfully tested for functionality, extending Voyager 1's life by 2 to 3 years. Operating the backup thrusters requires limited power for heaters, and if the power runs out, Voyager 1 will switch back to the original set. Similar plans were considered for Voyager 2. Engineers also address fuel residue accumulation in both spacecraft's thrusters to ensure proper antenna orientation. By allowing the spacecraft to rotate further before using the thrusters, they aim to extend their lifespan by at least 5 years, reducing the risk of clogs. The software update and adjustment of thrusters for both Voyager 1 and Voyager 2 were significant enhancements to the spacecraft system. They improved communication by adjusting thruster rotation and reducing firing frequency, ensuring better alignment with Earth for reliable data transmission. Additionally, these adjustments helped reduce propellant buildup in inlet tubes, extending the thruster lifespan by preventing clogs. The changes aim to optimize data return using fewer but longer thruster firings, though occasional data loss may occur due to increased spacecraft rotation. Engineers estimated that these measures would keep the thruster inlet tubes unclogged for at least 5 more years, allowing continued spacecraft functionality and further exploration in interstellar space. Overall, these updates were critical for maintaining operational efficiency and extending the mission lifespan of the Voyager spacecraft, enabling them to continue providing valuable scientific insights from distant parts of the solar system and beyond. Aaron Cummings, a software developer, discussed in a conference talk 2019 the challenges of communications with Voyagers 1 and 2. The team uses the Deep Space Network, a system of radio antennas plotted on different parts of the Earth, to communicate with the probes. Engineers carefully manage communication by sending specific commands and decoding signals despite the distance. In 2020, Voyager 2 faced a temporary anomaly that triggered an autonomous fault protection routine, leading 5 operating science instruments to shut down. However, NASA's engineers swiftly responded, restoring Voyager 2 to normal operations. The spacecraft's fault protection system was crucial in safeguarding its functions during this incident, and despite the temporary setback, Voyager 2 resumed taking science data, and the mission operators reported stable communication between Earth and the spacecraft. In March 2022, Voyager 1 started sending back nonsensical data, which resulted in many space enthusiasts assuming that the spacecraft was being held and hacked by aliens. It turns out that the culprit was not aliens but a routing error. The false alien message glitch with its Attitude Articulation and Control System, AACS, was when it sent confusing information about its health and activities to mission controllers. While the spacecraft seemed to function normally, Voyager 1's strong signal likely meant that the antenna was still pointed correctly and that the spacecraft was in safe mode. But it inexplicably sent its telemetry data through a different onboard computer that had stopped working years ago. This no longer functioning computer corrupted the information, making it appear not very sensible to the mission control team. The good news is that NASA engineers resolved the issue following their initial post about the AACS error. They essentially issued a restart command, instructing the AACS to resume sending data through the correct, functional computer. This restored the flow of clear and accurate telemetry to the correct computer. Then, engineers sent software patches to both spacecraft. This preventative measure is called an insurance policy. It aims to safeguard their operations and the flow of valuable scientific data from interstellar space. Voyager 2 received the patch first as a test due to its closer proximity to Earth. The successful test ensured the patch wouldn't harm Voyager 1, which holds critical scientific information and is farther away. Due to the age of the spacecraft and communication delays, there is a risk that the software patch could inadvertently affect essential code or operations, prompting meticulous testing and verification procedures by the engineering team. The reason the AACS started using the wrong computer remains a mystery. However, the leading theory is that another onboard computer might have sent a faulty command to the AACS, causing the routing error. While the team was still figuring out why AACS started using the wrong computer, another communication error happened just last year, around November 2023. This time, the problem was in the spacecraft's Flight Data System, FDS, which encountered an issue that prevented the spacecraft from sending scientific and engineering data back to Earth. In computers, ones and zeros are the fundamental language, a language NASA's enduring Voyager 1 spacecraft utilizes to communicate with its Earth-based team. However, Following a glitch affecting one of its onboard computers, Voyager 1's messages became nonsensical. The glitch with the FDS failed to establish proper communication with the spacecraft's telecommunications unit. Consequently, NASA reported that no scientific or engineering data was transmitted back to Earth. The FDS gathers data from Voyager 1's scientific instruments and oversees the spacecraft's health. It then transfers this data to the probe's telecommunications unit, the TMU, for transmission home. The Voyager 1 team detected the glitch when the TMU started transmitting a repetitive pattern of ones and zeros, suggesting it was stuck. Initially, engineers attempted a simple solution, restarting the system. However, this approach proved unsuccessful. Consequently, NASA undertook a more comprehensive troubleshooting process to resolve the issue. On March 3rd of this year, the Voyager mission team noticed a distinct signal from one part of the FDS, which differed from the rest of the data stream the computer was sending. Initially, the team needed to figure out what to make of it, since the signal wasn't in the usual format used by Voyager 1 when the FDS was functioning correctly. However, an engineer from the Deep Space Network managed to decode the signal and discovered that it contained a complete readout of the FDS memory. This memory includes the code, which provides instructions on actions and variables that can change based on commands or the spacecraft's status. Additionally, it holds scientific or engineering data for transmission back to Earth. The team compared this new readout with the previous one to identify any differences in the code or variables, helping pinpoint the ongoing issue. The new signal resulted from a command sent to Voyager 1 on March 1st, referred to as a poke by the team. This command was intended to gently encourage the FDS to attempt different sequences in its software package to bypass any corrupted sections. Due to Voyager 1's immense distance from Earth, approximately 15 billion miles, 24 billion kilometers, signal takes 45 hours round trip. Consequently, the team received the command results on March 3rd, started decoding the data on March 7th, and confirmed the memory readout on March 10th. The team scrutinized the readout and formulated a potential solution based on this information, though implementing it required additional time. Just on April 22, 2024, NASA's Voyager 1 spacecraft resumed sending usable data about its engineering systems for the first time since November 2023. 5 months after the issue occurred, the team discovered that a single chip responsible for storing a portion of the FDS memory, including some of the flight data system, FDS computer's software code, was not working, causing the issue. The loss of that code rendered the science and engineering data unusable. They could not repair the chip. They divided the affected code into sections and stored them in different locations in the FDS memory, adjusting the code to ensure it functions as a whole. The team began by relocating the code responsible for packaging the spacecraft's engineering data on April 18th and received confirmation of its successful modification on April 20th. In the coming weeks, they will continue to adjust and relocate other affected portions of the FDS software, including those enabling the spacecraft to return science data. These aging probes, which had been operating for nearly 50 years, presented a complex set of issues that tested the engineers' skills and ingenuity. One was the reliance on outdated documentation and manuals from the 1970s, which needed to account for the problems that arose after decades of operation. Furthermore, the engineers had yet to anticipate the wide range of challenges that would arise from the Voyager's extended mission duration and the damaging effect of radiation on the Voyager's hardware and electronics added to the situation's complexity. Any fix requires sending a command that takes 22.5 hours to reach the spacecraft and another 22.5 hours to receive a response. This 45-hour delay forces engineers to be extremely cautious with their attempts, as there's a limited window for troubleshooting in a reasonable time frame. Essentially, they're working with outdated information on a complex system from a vast distance, making a solution all the more difficult. In addition to ongoing struggles with these data glitches, scientists have been trying to manage and maintain the spacecraft's functioning for extended periods, switching various instruments inside the spacecraft. As of 2024, the Voyager spacecraft has strategically switched off various instruments to conserve power and extend its operational life. Voyager 1 and 2 have been operating far beyond their original mission duration. To manage diminishing power from their radioisotope thermoelectric generators, RTGs, the mission engineering team has turned off non-essential subsystems and heaters, focusing on reserving power for critical scientific instruments. Despite the gradual decrease in available energy, science instruments have yet to be deactivated due to power constraints. The Voyager spacecraft's end mission is expected to involve a gradual shutdown of their scientific instruments to save power. By 2025, all instruments will be switched off, and only occasional weak electronic signals will be detected, showing the spacecraft's position beyond the solar system for a few more years. Voyager 1 and 2 are predicted to continue transmitting signals until around 2036, depending on their remaining power. Voyager 1's last message to Earth is estimated to be received sometime in the mid-2030s. Probably more terrifying than the messages the Voyager might have sent back to Earth is the truth that after more than 47 years, the faint whispers of these spacecraft that we're hearing will turn into dead silence. Voyager 1 and 2 are already on a one-way journey out of our solar system, traveling faster than anything ever built by humans. They're not coming home, they're boldly venturing into interstellar space, the vast ocean between stars. But they're going full-handed. Tucked on board is the Golden Record, a message in a bottle for any alien life that might come across it. The Golden Record is a 12 inches, 30 centimeter diameter phonograph record made of copper plated with gold. This disc was carried on both Voyager 1 and 2 spacecraft and prepared by a team headed by Carl Sagan, a renowned astronomer, astrophysicist, cosmologist, and science communicator. Sagan wasn't directly involved in engineering the Voyager spacecraft. Still, as a visiting scientist at NASA's Jet Propulsion Laboratory, JPL, he introduced the idea of including a message for potential extraterrestrial life on board. He played a crucial role in selecting the content for the Golden Record, ensuring it effectively communicated the beauty and diversity of life and culture on Earth. The Golden Record is a remarkable compilation intended to showcase Earth's diversity of life and culture. It contains 115 images capturing landscapes, animals, and humans, along with greetings spoken in 55 languages. Additionally, there's a 12-minute montage of natural sounds and 90 minutes of music from various cultures and eras as of 1997. Written messages from then U.S. President Jimmy Carter and UN Secretary-General Kurt Waldheim are also included. To ensure universal understanding, NASA devised a code based on hydrogen, the most abundant molecule in the universe. Instructions on the record cover explain how to play it using binary code and rotation speed. The primary aim of the Golden Record is to serve as a time capsule, carrying a message about Earth to any potential alien civilizations that may encounter the Voyager spacecraft in the future. It reflects humanity's hope for interstellar communication and understanding. The Golden Record's significance lies in its comprehensive representation of humanity and our planet. It embodies a message of peace, scientific curiosity, and cultural richness sent out into the vast expanse of the universe. While the likelihood of aliens discovering and interpreting the record remains uncertain, it holds profound symbolic value as an expression of human curiosity and our longing for connection with other beings beyond our world. As Voyager concludes its mission to Earth, it embarks on a new journey that involves carrying the golden disk into space. This disk holds a message intended for potential interstellar civilizations, inviting them to discover the existence of other beings in the vast expanse of space. While the end of the Voyager missions may bring a sense of loss, their legacy of scientific exploration and their message to the universe will persist. How long do you think Voyager 1 will continue communicating and transmitting data? What are your thoughts about other interstellar beings finding and decoding the golden disk each Voyager spacecraft carries? Please share them in the comments below. Remember to like, subscribe, and hit that notification bell for more space exploration content. See you next time.